Good day, everyone. So today we shall be looking at another topic, photoelectric effect. Last time we talked about energy quantization of electron. So today we want to look at photoelectric effect about the same electron. Now, when you talk about the word photo, it deals with light. And then what is the effect of light on electron? The word electric there is taken from the root word electron. Now, the effect of light on electron, that is what make up photoelectric effect. Now, by the definition, we can say that photoelectric effect is a phenomenon where electrons are emitted from a metal surface when light falls on that metal surface. That is when you have the effect tag photoelectric effect. You could see here that this is a ray of light falling on this metal surface here, and as a result of that light falling on this metal surface, some electrons are emitted going to this direction. Okay, so these other ones are the emitted electrons coming from the surface of the metal as a result of the light falling on the metal surface. Now, these emitted electrons that are going this direction are known as photoelectrons because they are produced, the electron produced as a result of what? Photo, light, light. Now, the energy at which this electron is moving, these photoelectrons are moving, is known as kinetic energy. And by formula, it is given as kinetic energy, that's capital E, to be equal to HF minus W, where the H represents Planck constant, it's a constant value, and then the F is the frequency of the electron. The W is the work function. Now each of them has their definition. Now of course the E there is kinetic energy. We know what kinetic energy is, energy due to motion. Now the work function with that W is the minimum energy that the electron requires before it can leave the metal surface. Now that energy that the electron on the surface of the metal must gain before it can leave the surface of the metal is called the work function. And then the threshold frequency is the lowest frequency that makes light or photo to emit electrons from the metal surface. Now, the frequency of this light ray, that minimum frequency that the light ray needs to emit electrons from the surface of the metal is what we call the threshold frequency. And then when we have the threshold wavelength, the threshold wavelength is the longest wavelength that will produce photoelectrons. Okay? So the longest wavelength by the light ray that will help us to produce photoelectrons. So by formula, kinetic energy of the electron equals to product of Planck constant and frequency of the light ray minus work function. Okay, that is the minimum energy that the electron needs. That formula is very key in solving problems. And we also know that threshold frequency is equals to velocity of light, that's C, over threshold wavelength, that is lambda naught. So please, let's take note of these formulas to solve problems. Now, what are the areas of application of S-ray? S-rays are used in burglary alarm. They are used in television cameras. They are also used in automatic devices like switching of light, just like the street light we use on the street. At night, you just see that the light turns off. It's as a result of what? S-ray. It's used in production of sound in films, in film and track, and it's also used in industrial controls and counting operations. Okay, so having known that, let us see some calculations based on the formula we talked about earlier. Example 1 says, compute the frequency of the photon. Photon means light, we said earlier, whose energy is required to eject a surface electron with a kinetic energy of 3.5 times 10 raised to the power minus 16 electron volt if the work function of the meter is 3.0 times 10 raised to the power minus 16 electron volt. And we are given Planck constant, which is H, to be 6.6 times 10 to the power minus 34 joule seconds. And then we are told that 1 electron volt equals 1.6 times 10 to the power minus 19 joules. Now, as we our method of solving our problem, we write out our parameters. First of all, we are given the kinetic energy, which is E now, capital E, to be 3.5 times 10 to the power minus 16 electron volt. Okay, we are given our work function. Okay, our work function, which is W, to be 3.0 times 10 to the power minus 16 electron volt. And we have to compute the frequency. That the frequency is unknown here. So by formula, we know that kinetic energy equals to Hf minus W. So making your F subject of the formula here, we have F to be equals to E plus W over H. Now coming here to substitute those values, the value of E we know is 3.5 times 10 to the power minus 16, is it here? Then plus the value of W we know is 3.0 times 10 to the power minus 16. All are in electron volts, so we open and close bracket and write our electron volts all over the Planck constant, which is H, and that is have been given to be 6.6 times 10 to the power minus 34. Okay, now going forward, we know that 1 electron volt is 1.6 times 10 to the power minus 19. Instead of having electron volt here, we substitute it with the value of 1.6 times 10 to the power minus 19 here, and this gave us this fraction. So when you simplify this fraction with your calculator, you'll be having the frequency, that our F now, to be 1.58 times 10 raised to the power minus 1 Hertz. So that's it. So that's one way we can apply the equation we talk about. Let us see another example on this. It says the work function of lithium is 3.30 electron volts. Calculate 1. The maximum energy in joules of photoelectrons liberated by light of wavelength 3.3 times 10 raised to the power minus 17 meters. Okay, 2. The threshold wavelength of the metal. Okay, so let's write our parameters so we know what we are looking for. Firstly, we are told that the work function is given, that is 2.30 electrons, that W is 2.30 electron volt. Now, we don't use electron volt when solving problem. We need to convert it to joule. So 2.30 electron volt to joule will now be 2.30. 1 electron volt is 1.6 times 10 to the power minus 19. So multiply it. So the work function in joule is now 2.30 times 1.6 times 10 to the power minus 19 joule. Again, we are given wavelength, okay, the wavelength of the light to be equal to, wavelength is lambda by symbol, to be equal to 3.3 times 10 to the power minus 17 meters. And then we have to find the maximum energy, that is our E, capital E, and also the threshold wavelength, that's our lambda naught. So by formula, we know that our maximum energy, which is our kinetic energy, is equals to Hf minus W. But Hf itself can also be expressed as Hc over lambda, okay, minus W. Now, going forward now, we now substitute all of this, we now substitute the values of all of this into the equation. Now, our H is 6.6, the constant, 6.6 times 10 to the power minus 34. Our C is the speed of light, that is, it's also a constant, 3.0 times 10 to the power 8 all over. Our lambda is given here to be 3.3 times 10 to the power minus 17. Then minus our work function, which is this, and it has been converted to this, to be 2.30 times 1.6 times 10 to the power minus 19. Okay, now when you pick up your calculator and simplify all of these, our maximum energy will be 6.0, approximately 6.0 times 10 to the power minus 9 joule. Now, second question says we should calculate the threshold wavelength of the meter. By formula also, work function is Hc over threshold wavelength. Now, making threshold wavelength or subject the formula here, Hc, our threshold wavelength will now be equal to Hc over W. H is a constant, C is a constant, because this is Planck constant, this is speed of light constant. So we substitute the value here all over the work function, which we are giving here to be 2.3, but in joules is this. So we substitute it here as well. And when you simplify all of this with the calculator or using your law of indices, you have your threshold wavelength to be 8.61 times 10 raised to power minus 7 meters. Okay, let us talk about another area of application of this photoelectric effect. We mentioned the application earlier before coming to examples. Now let's talk about another key area of photoelectric effect, and that is X-ray. X-ray are actually produced when you could see just the same way we talk about photoelectric effect. So X-ray are produced when um they are produced when high potential difference of heat is applied. Okay, so they are produced when high potential of heat is applied, and the light now falls on the metal. These emitted electrons are what we call the X-ray. Okay, but then it must be this time around, for you to get X-ray, the metal surface must be a filament. Okay, must be a metal filament, and then when the light falls on it, then the electron that emit out of it is what we call X-ray. Now this X-ray that are produced, of course, are now stopped by a tungsten. This target here is called a tungsten. The one that now stop the X-ray produced. Okay, so the X-ray are produced when a hot filament are heated up by electricity. Okay, and when it's heated up, you see the emission of X-ray, which are stopped by tungsten. All right, now it was discovered by a scientist called Williams Röntgen in 1895. And these X-ray are of two types. We have the hard X-ray and the soft X-ray. The hard X-ray are the ones that have high penetrating power but low wavelength, while the reverse is the case for soft X-ray. The soft X-ray have a low penetrating power but a longer wavelength. So just the same way we produce photoelectrons, that's the same way X-ray are also produced. The only difference here is that instead of using light, okay, instead of using light to heat up the filament, we use electricity to heat it up. And when you heat up the filament, the X-ray are now produced. But then we are still talking about the liberation of electron from the metal surface. Okay, now let's mention some properties of this X-ray. Number one, this X-ray are electromagnetic wave. Okay, they are electromagnetic wave of high frequency, and they have a short wavelength of 2 times 10 this is power minus 10 meters. This is power of minus 10 meters, and they have high penetrating power. That is the hard X-ray. Now they also travel in a straight line, and they are not diffracted by electric or magnetic field. That means they don't have charge. They have no charge. Okay, they are not diffracted by crystals as well, and they ionize gases, and they also cause zinc sulfide to fluoride. So these are the properties of X-rays. Okay, now let's talk about application of X-rays. We use X-ray for examining body to locate broken bones. Okay, because of its high penetrating power. You could see here when the X-ray are produced, you could see immediately it penetrated this mass and the bones were visible because of what? Its ability to penetrate, its high penetrating power. So because of the high penetrating power too, you can use X-ray to detect contraband in a bag, okay, because it can penetrate. They are used to detect cracks as well in a welded joint, and they are used for investigating crystal structures They are used for treatment of tumors and malignant growth in the body, and they are used also in killing germs in agriculture. But however, in as much as we have good application of X-ray, X-ray also have its own hazard. Okay, X-ray, if it's not well handled, it can cause genetic mutation. If you have excessive X-ray in your body, it can cause sudden change of gene. That's what we call mutation. So it can cause genetic mutation. It can also destroy the body cells. It can cause leukemia, that's the cancer of the blood. It can also cause skin burn when it's too much. When you expose yourself to X-ray for long, it can cause skin burn and cancer. So for us to avoid this hazard, it is good that you put on lead coats and also go for regular medical checkup, okay, to avoid the hazard of X-ray. All right, so we are going to be doing the cutting here. Thank you for listening. Bye for now.